In order to complete the whole convolution stack, we need to help the image undergo convolution operation, non-linearity, and pooling. So CNP. There are a lot of terminologies, but I think these terminologies are very straightforward, very simple. You should write these down and you should cover them in this particular sequence in order to learn CNNs the best, in order to build a decision-making head. So that decision-making head might be capped with softmax or any other activation function to push everything into probability mass or probabilities that will help us take some sort of classification decision using the CNN. Welcome to Deep Learning Talk. So this lecture or this session, we're going to talk about how do we study convolutional neural networks, which is CNNs under deep learning, and what should be the mental model to study CNNs, to understand CNNs, and to understand all the concepts under CNNs. What should be the subtopics and what should be the approach? So the first thing that we should focus on doing or building is building the fundamentals, building the core idea, and building the intuition behind CNNs. The first thing that comes to my mind is understanding computer vision, largely the rise and impact of vision, the rise and impact of images, and the adoption of everything that has to do with images. You first understand theoretically what is convolution with respect to two discrete functions. What is the convolution operation between two discrete functions? So we generally do a convolution between an input image and the filter. So filter and kernel we use interchangeably. There shouldn't be no confusion in that idea. Now the convolution produces an output. The operation convolution produces an output known as feature map. So we should get comfortable with the whole terminology and the AI literature here. So we have introduced three terms right now. Input image, we know that it's nothing but pixels. It can be multi-channel image, basically RGB channels or grayscale image. Then the image has to undergo the convolution operation. A filter or a kernel has to convolve over the image to produce a feature map. So there are three terms that we have to get comfortable here with: filter, kernel, and feature map. Filter and kernel are used interchangeably, and feature map is something which is produced, which is the better representation of an image in a different coordinate system, right? Then the main idea is to study the idea of adding nonlinearity using ReLU. Now, why do we add a nonlinear activation function on a feature map? Because convolution operation is a linear operation. We need to add synthetically some nonlinearity. We use ReLU for adding nonlinearity. Then we have to perform one more operation known as pooling. So, in order to complete the whole convolution stack, we need to help the image undergo convolution operation, nonlinearity, and pooling. So CNP. After that, we can say that the whole convolution stack is completed, and now we have some non-linear representation, which we can maybe call as features, right? So now we understand what is non-linearity, how it is added using ReLU. Then now we also understand what is pooling, the idea of why we need to pool. So we generally pool to downsample. So we leverage multiple techniques to pool. Two of them, two very famous are max pooling and average pooling. We need to understand what is max pooling, what it does, what is average pooling, what it does, and how does it downsample the original feature map, and what are the advantages of pooling. We also have to get comfortable with the idea of padding and stride. So in the convolution operation, we use something known as padding. It's basically when we want to cover all the boundaries, or you can imagine the bezels or the corner boundaries of an image. And stride is the step size that we want to, is basically convolving a small filter, maybe a 2 by 2 or 3 by 3 filter on an image. So stride helps you decide the step size of your sliding window. So your convolution filter is going to slide over the image step by step, like a sliding window, but on a two-dimensional sliding window, not a one-dimensional sliding window. So stride helps you decide the step size, right? So there are a lot of terminologies, but I think these terminologies are very straightforward, very simple. You should write these down and you should cover them in this particular sequence in order to learn CNNs the best, right? We need to understand that we can stack multiple of these convolution blocks together in order to build a complex architecture. The idea behind stacking multiple convolution blocks together is to develop a sense of deeper and hierarchical feature extraction, to extract deeper and hierarchical features. So, just like you can think about it with respect to neural networks. So, like in neural networks, we always stack multiple hidden layers to prove that we will have deeper understanding, richer understanding of the whole data set with multiple hidden layers. Similarly, here we stack multiple convolution blocks together in order to build a deeper and hierarchical understanding of features on the images, right? After we are done with the convolution stack, Now we need some decision-making module, which is our fully connected layers, right? So we stack multiple linear layers or the fully connected layers. So here, think about fully connected layers as a traditional neural network, a deep neural network, an artificial neural network, a multi-receptron, right? Think about the whole idea or the architecture of CNN as uh, some convolution block and some fully connected layers. Now, these fully connected layers are very analogous to a traditional neural network, right? So we kind of flatten all the feature maps and feed it to the fully connected layers in order to build a decision-making head. So that decision-making head might be capped with softmax or any other activation function that will squish everything into probability mass or probabilities that will help us take some sort of classification decision using the CNN. So can we say that CNN is just a combination of the convolution block and a feed for a neural network? Why not? Right? So the only new thing for someone who knew neural networks is going to be the convolution block, right? But for someone who does not understand neural network, there are going to be a lot of challenges in understanding CNNs because CNNs have a downstream dependency on neural networks. Neural networks have a downstream dependency on other classical machine learning algorithms, maybe like logistic regression and linear regression, and activation functions and loss functions. So if you don't understand the idea of neural networks, it's better you skip CNN for now, right? You only come to CNN once you understand the idea of neural networks, the feed forward pass in classical neural networks, the backward pass, the idea of gradient descent, the loss functions, which is the cross entropy loss and the mean squared error. Only come to CNNs once you are ready with solid fundamentals on neural networks. Right, because there's no point in studying CNNs if you don't understand classical neural networks or deep neural networks, right? Okay, now the mental model is very much clear. The subtopics and all the topics under CNNs are very clear. Now let's talk about the idea of implementation. Like, how do we master the coding methodology or the implementation methodology for CNNs, right? So if we want to do everything from first principles, the idea is to implement every operation from scratch using maybe the classical libraries like NumPy, right? You pick up a simple data set and like MNIST or Cypher 10, which has 10 classes, and you build a CNN, a very simple architecture of CNN with one convolution block from scratch. So when you have to build one convolution block, or when you have to build the whole architecture from scratch, what I mean by that is you write all the components from scratch: the padding operation, the pooling operation, the max pooling or average pooling, depending on which pooling you are using, the ReLU function, the flattening function, feed forward neural network layers, the forward pass and the backward pass, and the whole training function, right? So this is basically the first phase or difficult way, the hard way to do things, right? You implement every component from scratch because you will get the understanding of CNN from the first principles. And the second phase, or let's say a little easier one, but also very meaningful, is why don't you build an architecture of a CNN in PyTorch, right? You use all the PyTorch NN module function to build a CNN, right? And you can use the existing optimizer that is there in PyTorch, and you can write a training function, the feed forward pass, and the predict pass. Just take help of PyTorch and everything that is available in the neural network module. And using that CNN, you can again train on a simple data set, right? Now, the third phase is now that you're comfortable with the architecture of CNN, now you know all the operations under CNN, why don't you pick up an existing state-of-the-art CNN and maybe retrain it or fine-tune it on a smaller data set, right? So let's say you implement a small VGG16 architecture in PyTorch and you retrain it or basically train it on Cypher 10, right? So this is going to help you get familiar with existing state-of-the-art architectures. So VGG16 today might not be the state-of-the-art, but it is going to help you understand all the existing CNN-based architectures like VGG, like ResNet 50, and different variations of them. So pick up any one of them and just build the architecture using PyTorch and train it on a smaller data set. You know, the mental model of transfer learning and fine-tuning. You pick up a pre-trained model from the PyTorch library and fine-tune it on a smaller data set like Cypher 10, depending on your computing power, your storage. I'm guessing, assuming that you might have access to Collab, a single GPU instance, or maybe your local machine like a MacBook Pro or some decent machine. So just use a smaller data set, leverage a complex model, a pre-trained model like a ResNet, and pick up a smaller data set from Kaggle or the Cypher or MNIST and fine-tune it on that particular data set, right? So these 3, 4 coding methodologies can help you learn different dimensions of CNN at the end, you can build a real world CNN project or a typical CNN project. Maybe you are performing a classification problem and you're classifying images. Now, those classification problem can be detecting X-ray images or detecting pneumonia of X-ray images, detecting diabetic retinopathy from the retina scans, or doing some sort of classification task on an existing data set. I think this would give you a solid understanding of learning CNNs from scratch. Thank you.